Today we're going to be looking at another video by Subject Zero Science, specifically the thorium problem, why it may never happen. And I like Thor's little hammer there. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see what this is about.
Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It can be used in liquid.
That is correct. Thorium does have higher natural abundance, but it can't do the job by itself. It needs to be paired with a fissile material to work. Fissile material like plutonium, or uranium for that matter.
Fluoride thorium reactors to produce electrical energy, heat, and other valuable products. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand.
That's true, though you can also do that for, say, uranium or plutonium. Now, he's talking about the lifetime for your individual, or probably even for your household, with you, your spouse, and 2.4 kids, or whatever the average is. So, yeah, that's true.
It's been over a decade since thorium energy was introduced to the world by Kirk Sorensen and
I'm not familiar with that person, but thorium has been thought of as an idea for a very long time. I think we're getting close to 70 years, if not more than that at this point.
Became an instant phenomenon. Up to that point, the future of nuclear energy was bleak and uncertain, as power plants all around the world were being shut down and any new development was completely halted. Thorium.
Fortunately, we've turned the corner in recent years with, say, Vogel's 3 and 4 showing up in the state of Georgia and recent new sites in Finland, UAE, China, to name a few. So not where we need to be, but I think it is looking better than 10 years ago for sure.
Was a promise of a fresh start in an industry plagued by monumental accidents.
Plagued by accidents, more like plagued by the public exaggeration to said accidents. There are way more accidents, say, due to cars, but not as many people go after the automotive industry, for instance. And far more fatalities and severe injuries from those. Not to downplay Chernobyl, for instance. Chernobyl was a horrific accident that did not need to occur, and there are other less severe accidents, but compared to, say, car crashes, plane crashes, compared to, say, car crashes or other generation methods such as coal or natural gas and the pollutants they emit, the radiation they emit, it's just not the same. Or showing pictures of Chernobyl.
But what is the thorium promise? Thorium promises all nuclear energy benefits.
I've actually never heard the term thorium promise. If it is a promise, it's something that I haven't seen, which is telling, considering how long I've been in nuclear.
And more. Cheap and abundant, with the same energy output as conventional nuclear power plants, safer and easier to maintain, and above all, no atomic weapons. Of course, we now know that some of these claims are a bit exaggerated.
No atomic weapons, okay? Let's see.
However, whatever thorium energy promise is far better than what we have today. Why we don't invest more into it is a complex issue. Long story short, it all starts with the thorium power plant design.
I would even say it starts before that in established uranium industry and infrastructure that was used to make nuclear weapons after World War II. There was the established supply chain and infrastructure for enriching uranium to make weapons. So you can argue uranium had the first mover advantage. There's one thing that's interesting is Little Boy, the very first atomic bomb that was built, had well over 90% of the world's supply of uranium-235. That's because there wasn't that much uranium-235 at the time, since that's all it was used for. But it's like, hey, we know how to make uranium-235, and we don't need to enrich it nearly as much as we do to make nuclear power plants. So the point is, they've had a first mover advantage that was pressed.
It is basically divided into 3 parts.
This is a cool
The
model.
reaction core located inside the containment building, power generation building, and chemical processing plant.
That is a really cool little 3D model he made. Thanks for recommending this video. This one has some really cool effects. Beautiful way of visualizing a simple one-line diagram of the nuclear power plant.
A thorium power plant isn't that much different from a conventional one, except for the chemical processing plant. There are many proposed technologies to develop a thorium power plant with, but the most famous one is the liquid fuel thorium reactor concept.
Okay, the chemical processing plant to make the liquid fuel. Got it.
Or lifter, which is the technology I will focus on this video. Power generation portion is just like any other, but the core and chemical processing plant are special.
When he says just like any other, we're talking uranium-based nuclear power plants, natural gas plants, coal power plants, anything that uses a steam cycle. Nuclear fusion plants will likely use a steam cycle if we could make a commercial nuclear fusion. But yeah, that bit's very similar. It's been very similar for the past 200 years. Only real difference between nuclear and coal or natural gas is turbines are typically bigger.
Completely different from conventional nuclear cores. The reactor core is basically designed
Look at this.
to have two liquids flowing through it. The first one is the blanket salt comprised of lithium, beryllium, thorium fluoride. This liquid goes around the core for reasons that I will explain in a minute. The second fuel salt comprised of lithium, beryllium, uranium fluoride goes through the core. The fuel salt is responsible.
So this is pretty exotic. You could technically use it in a typical light water reactor, though the fuel is going to need to be mixed with uranium and plutonium, because again, thorium can't do the job by itself. Essentially, the thorium-232 absorbs a neutron, becomes thorium-233, and then undergoes a couple of beta decays to get to uranium-233, which is fissile. Which is why thorium-232 is called fertile, because when exposed to a neutron field, it can turn itself into a fissile material to sustain your reaction. But yeah, light water reactors wouldn't work with just pure thorium. They're mainly designed for fast breeder reactors. A lot of them I've seen have typically involved using liquid sodium. There's some weird ones out there that could use liquid lead, which is a bit ironic because you normally think of lead as absorbing gamma radiation, but here we're talking neutrons. So you can get one to work that way, or using a molten salt reactor. So those are the typical ones based on how they work, but as you can see in this example, we're using thorium and uranium. Thorium does need a little bit of help to get going.
Responsible for causing the chain reaction inside the core, to which some of the neutrons expelled by uranium is absorbed by the blanket salt, transforming thorium-232 into thorium-233.
Yep.
This new fuel is then transported to the chemical processing plant, located not too far from it, and goes through a series of filters with various purposes. Processing the newly formed fuel is a complex task that uses several filtering techniques with careful handling of a liquid that not only is extremely hot, but also in active nuclear decay. While the chemical processing plant is a marvel of engineering, explaining each step goes beyond the scope of this video.
So what's interesting is chemical processing is used in conventional nuclear power plants, and yes, and not just say to keep your water's pH, conductivity, and band, like you use chemical processing for any large power plant or industrial facility that involves using water in pipes. It is used for reactivity control as well in a conventional nuclear power plant. So expect this to work somewhat the same way operationally, although kind of backwards. See, in a pressurized water reactor, such as the plant that I worked at, it isn't just water. It's water with boric acid in it. Think of boric acid as the opposite of fuel. It adds negative reactivity because boron absorbs neutrons instead of the uranium. So it slows down your reactions. It's liquid control rods. So performing a boron injection will actually slow down your reaction and is used in tandem with control rods for reactivity control. because they slow down the reactions in different parts of the core. Simply inserting control rods by itself is not optimal, because that will just push the power distribution down to the bottom of the core, whereas boric acid is in solution with water, so it's going to give you a more even distribution at working in tandem with the control rod, as well as lowering turbine load. It's all about keeping a balance. So what's interesting is, operationally, having the fuel directly in something like that could work the opposite way, which is fascinating.
What I want to focus on is where the setback starts. In summary, thorium-232 absorbs a neutron from fission and becomes thorium-233, which decays quickly with a half-life of about 22.3 minutes.
That's the other reason why thorium doesn't work by itself, because like, okay, where are you getting these fissions from? That's why you have neutron sources such as americium-242, as well as enough fissile uranium or plutonium, depending on design, to get enough of a neutron population to create a sustainable chain reaction.
By emitting a beta particle and transforms into protactinium-233. At the last step is where we have the biggest drawback, which is separating protactinium-233 from the newly formed fuel salt. Protactinium-233 decays in about 27 days to uranium-233, also by emission of a beta particle. However, there are numerous issues in this step. First, protactinium cannot be exposed to neutrons, or else it will transform into uranium-234, which is undesirable since it is in fissile material. So
yes, protactinium-233 does absorb neutrons, so it kind of has that same effect, although when I talked about boron, though not nearly as much. It's not going to, say, shut down your reactor as quickly, but the point is you have to have a sufficient population of neutrons. Interestingly enough, uranium-233 actually has a slightly higher reactivity than uranium-235. Not as much as plutonium-239, which does actually show up in conventional nuclear power plants. You get more of that, and what's interesting is plutonium-239 comes from the non-fissile isotope uranium-238, absorbing a neutron, becoming uranium-239, which beta decays into neptunium and then plutonium-239, and that's more reactive than uranium-235 and 233, which is why reactions are typically faster at the end of a core life versus beginning of core life.
it is crucial to have a filtration up to 99%. Second, separation of uranium from protactinium involves injecting fluorine into the mix, transforming uranium tetrafluoride into hexafluoride, a gas. The gas needs to be captured and reduced back into tetrafluoride. Third,
fluorine being a highly reactive chemical, so there's additional chemical hazards, and liquid metals in general do not play that well with water, which you're going to be using on the secondary non-nuclear part of the plant. So if you have any leaks or any corrosion, degradation, maintenance gets more challenging, again, compared to a uranium-only reactor.
it takes about 2 months for 75% of the protactinium-233 to decay into uranium-233. The newly formed fuel is separated and goes into the core, while the remaining 25% stays decaying.
So it can take you a while to get up and going. Once you're operating on a continuous cycle, it's less of an issue, but there's a good bit of lag time when you're first commissioning, starting up your reactor. Okay.
On top of all of that, all chemical steps are done in extreme temperatures, otherwise it turns back into a salt and compromises the entire system.
That's hot. In Fahrenheit, the core exit thermocouples are a mere 620 or so degrees, which is still hot and highly pressurized at over 2200 psi, but still, this is more extreme than that. So again, this is a pretty out there reactor design. Not saying every thorium reactor has to do something like that. Thorium can be used to supplement nuclear fuel in a mixed oxide fuel with uranium and plutonium in a conventional nuclear power plant, and the thorium will really start to get its use middle of life, end of life, kind of similar to how plutonium is used in a uranium nuclear power plant. Now it's used because now plutonium isn't added. There's no plutonium in fresh fuel, it just shows up. which is interesting.
If done optimally, this process can be repeated forever, which, while complicated, eliminates the need to shut down the core to refuel.
That is nice, and there are nuclear power plants that use what's called a continuous fuel cycle, essentially that allows for online refueling, such as the CANDU nuclear power plants. Problem is, you're not going to run forever, even if you had a perpetual motion nuclear power plant, and that's because the turbine building does need to come down for maintenance. And when you have a massive temperature gradient, keeping this reactor at temperature and pressure online, you're going to flash your steam generators that power your turbine, and you're not going to be able to use them. So you will have to power it down to support a turbine outage. But you could conceivably keep it running longer. You could go upwards of 5 years compared to the 18 to 24 months. So that is a noticeable improvement.
Conventional power plants need to shut down every 18 months for a month to refuel.
A month's pretty spot on. It's actually at the fast end. There are times that doing other maintenance, not just the refueling part of the outage, can take longer. But yes, you can have an even greater capacity factor, or the time that the power plant stays on at 100% power with this type of design once you get it going.
The chemical processing plant is very complicated to design and maintain, and it is considered the biggest barrier when it comes to thorium energy development. Nevertheless,
again, you're focusing on just one reactor design. I think thorium can lend a helping hand, not just in this type of design, because this, can get complicated. One other thing to point out is a lot of plant operators and chemistry technicians really like working at nuclear power plants because you're not dealing with a lot of hazardous chemicals like fluorine, compared to, say, working in a petrochemical plant, for instance. So some of those people might not be as keen to work at this sort of plant. That's by no means a game breaker, but it's one thing that doesn't really get pointed out as much when looking at these sort of designs, is the stuff that the plant operators and the chemistry technicians have to deal with.
while it is complicated, rest assured that it can be done. As a matter of fact, the technology already exists.
It does.
At the end of the day, there are more pros than cons when it comes to thorium energy.
All right, let's see what they got. Pros: abundant resources, reduced nuclear proliferation risk. That one's actually debatable, because if you're looking at the thorium having to be paired with plutonium, plutonium's a lot bigger risk than using uranium. Like starting out with plutonium, because the plutonium that's produced in a fission reaction is located next to spent fuel, as in good luck getting it out of there. But here, I would say you might have a slightly higher proliferation risk. It's still absurdly low. I think nuclear proliferation risk is exaggerated throughout all aspects of nuclear power, including ones that use thorium, but I would say it does have an increased risk relative to uranium, but not very much. Improved safety, that's more of a function of reactor design than fuel design. Since thorium is seen as newer, you mainly see it paired with these liquid metal or molten salt designs that incorporate more passive safety systems, but they are also included in conventional designs as well, just the newer models. So improved safety, yes, but that's just by virtue of including more passive systems. The AP1000 pressurized water reactor, that's a light water reactor, would have this improved safety. Enhanced fuel, yes, that is a key advantage. You can have it supplement and play well with the uranium and plutonium, so you could even enhance the fuel with a few modifications to existing nuclear plants rather than a full-on conversion. Thorium can also play well in what's known as pebble bed reactors, where your fuel and your moderator are in these tiny little pebbles. And yes, they can use graphite quite safely, unlike Chernobyl. These can use both uranium or thorium, but thorium can play a lot better with this due to essentially the high neutron economy, with these little spheres maximizing your contact surface area. And graphite's an effective moderator. It has high thermal conductivity, so can effectively breed some uranium-233 from this thorium-232. And it's a lot more efficient from these things. It's a lot more efficient, so you're going to get a lot more out of your individual uranium-233 fission, which is more reactive than uranium-235 due to this shape. What's also nice is they are in individual balls, so you're less likely to have a cascading core melting event spread from one piece of fuel to another, because they can withstand very, very high temperatures. Longer cycle's a big one. Can be done with uranium too, but that's a big economic advantage right there. Diverse reactor designs, that could really go either way. You can argue it's diverse just because it's new. So cons. Infrastructure, yes, that's probably the biggest con, is having to make chemical plants and add hazardous chemicals to the mix. Because that's one of the nice thing about nuclear power plants is less hazardous chemicals compared to, say, coal or natural gas. Regulatory hurdles, it's new technology, so the regulatory hurdles are going to be quite massive. Competition with uranium, it doesn't have to be that way, because you can combine it with the uranium fuel cycle. But I think he's getting at more of the infrastructure has been well established. That's definitely true. And public perception, I'm not sure I don't think I agree with that. I would say it would have probably a more positive public perception than uranium, simply because it's a new way of looking at nuclear. I don't agree with that. I'd say both technologies are perfectly valid, but people, for whatever reason, still got the bad memories of things like Chernobyl and 3 Mile Island stuck in their heads, that having something a little different might actually have a more positive public perception. But what do you think about that? I actually think it could be higher with thorium. And most people who I've talked about, who are even kind of anti-nuclear, would say, but if you can get thorium reactors to work, that would be great. Not really knowing anything about nuclear, but that's the point. They seem to think it's something new and exciting that is somehow better. And it is better in some ways, but I don't necessarily think it should replace uranium, at least not quickly. It can work in tandem, but it's interesting.
Side by side, you can see that investing in thorium energy should be a no-brainer. So what holds?
Just a pros and cons list. You need to put some dollar signs on there if you're going to go by investing. Yes, there's 5 in the pros, but infrastructure and regulatory hurdles are massive from an investor because they take time. And especially a risky project, and by risky, I'm strictly speaking in terms of investment risk, things that can cause delays, people changing their mind until the site is built. Those are 2 big ones that are weighted even more than the one on the left. And yes, that includes abundant resources and longer fuel cycle.
This technology back. It comes down to basically 3 complications: regulatory hurdles, lack of investment, and competition. The nuclear industry is extremely regulated, and safety protocols must be designed for everything, even for problems that most likely won't ever happen. As you may know, small modular reactor technology was approved in 2020 and are commercially available since 2022. However, its approval came about after a 12,000-page document was submitted just for safety requirement, with a total project funding of about $600 million.
Engineering costs like that are staggering. Let me let go.
In other words,
engineering costs like that are quite staggering. However, recent legislation might make things go faster, at least within the United States.
For any serious thorium research and development, consider...
It was after this video was made, but President Biden just signed the Advance bill, which could cut the regulatory approval time for microreactors, which are smaller than SMRs, to 18 months. And it was bipartisan, so that's really encouraging. Reducing approval times has already gotten some companies to look at SMR deployment and microreactor deployment. Very exciting.
The same requirements as SMR technology. However, securing investment is next to impossible because of what I've believed to be the most challenging matter: the anti-nuclear energy lobby. Acquiring investors to fund any research is where the problem starts for anything really. Crowdfunding can maybe start your research, but as we saw...
A crowd-funded nuclear plant, never heard of that. I don't think it needs that. I mean, I don't think I've ever seen a crowd-funded like natural gas plant or coal plant, and Yes, there'll always be an anti-nuclear lobby, but there's a lobby for everything. So I don't think that's going to stop it. But lobbyists don't stop investors by themselves. At least not the good investors.
With SMR technology, I doubt crowdfunding would reach $600 million. So you're left with two choices: private investors or the government. Private investors are usually smart and require something back. Most of the time, they just want assurance of gains on their investment, which makes it extremely difficult to get their backing. Now you're left with the second choice.
You just got to show that they're going to get it back, and really, what's going to get it is a proven track record of being able to build these and crank them out on time. Because once you get nuclear power plants, especially SMRs and other things, and reactors that don't have to be shut down very often, they make a good bit of money. I'll pin a comment down below that talks a lot more about the economic aspect, but the hardest part is just getting them built. Once you get them built, they pay for themselves quite handily, and especially if they last their full lifetime, they'll make a lot more money than, say, a similar size coal or natural gas facility or facilities would make.
The government. But most of us know by now that governments aren't in the business of solving problems. However, they can be helpful in cases like this. They should know that thorium is a major problem solver for them.
What are the 9 most scary words in the English language? We're from the government and we're here to help. That's pretty funny.
The world. Catch is, some people are more concerned with their bottom line than fixing problems because of bad actors. While the job...
Bad actors? Well, it wasn't exactly the China Syndrome had Jane Fonda and Michael Douglas in it, so there you go, some bad actors. I know what he means, I just couldn't resist.
Of a scientist is to educate and rely on the good spirit of their elected officials to help them develop better technologies. Activists, especially the ones against nuclear technology, are by far the biggest drawback a thorium research company must face.
Yes. People that somehow coordinate nuclear power plants with nuclear weapons. Makes even less sense than people being against cars because they're also tanks somehow.
Greenpeace, among other organizations, actively fight against any sort of nuclear technology development. They work closely with politicians, advising them to stay away from it. But
yeah, they're a pretty big anti-nuclear lobby, but I wouldn't give them too much credit.
That's not all. Overcoming the anti-nuclear energy lobby is just the first step. Next, we need to battle our way up against the uranium industry, which is well established with an incredible infrastructure that dominates the sector.
Did I work for big uranium? Maybe.
The same infrastructure needs to be developed for thorium, something that most likely the uranium industry will fight tooth and nail against it. Because
you see, that's where business-savvy people could be the first with uranium. Use the infrastructure they have, because I mean, uranium is mined. Thorium will also be mined. It will be processed. I mean, the big thing is, there's a lot of money to be made in chemical processing patents for uranium technology and various reactor designs. I would see it as a big opportunity right there, and big uranium should go after it first if they want to survive.
Because they know that thorium is a major threat to them. Public perception is also
just a very limited way of thinking. Now, I'm not saying he's wrong and that these people don't exist. Of course, people like that do exist, but got to look at the opportunity. Maybe I'm too much of an idealist and an optimist.
A major issue. Though most Americans see nuclear in a positive light, 44% of people still opposed based on nothing more than fear, even though this technology is by far the safest and cheapest source of energy that
I've seen it with just because they give it and people are lumping it in with weapons. I've even seen that. Even as simple as how you phrase that poll, do you support nuclear versus do you support nuclear power? Adding that extra word because they could think you're talking about weapons. I wouldn't look too much into polls simply because polls have their own biases in and of themselves. Like, I'm sure you'll find a Greenpeace poll that probably has it 88% people oppose nuclear.
Can ever be. It is safer than wind and hydro, only losing to solar, except that none of them come even close to the energy output capabilities of nuclear.
I've seen it actually close to solar. How people die from wind is falling off of turbines, and solar is about the same, though it may go up as solar gets used more, because how you die from solar is you fall off of roofs or you get electrocuted, which getting electrocuted is a hazard associated with any sort of energy production. And a lot of the deaths from nuclear are more of industrial accidents that you see at any sizable facility. For the size of facilities and the number of personnel hours worked, their safety record is far better than wind and solar.
Though the future of thorium seems mostly uncertain, there are countries that invest in this technology. I'll be honest, I'm very skeptical of whatever China is doing. My bet is that India is leading the way, and maybe we could have thorium energy soon. After all, they hold the largest reserve of thorium in the world, which is a huge.
I hope we see more of it too. It doesn't have to compete with uranium. It can be part of a well-balanced and well-hedged nuclear portfolio. Thanks so much for the recommendation, and thank you very much for watching. I'll see you next time.